Here is an interesting fact to start off the video. The fastest recorded speed for a man-powered aircraft is held by the NASA X-43. It reached a speed of Mach 9.6, which is approximately 7,346 miles per hour. Anyways, the lesson of today's video is to go over the basics of static stability, especially in relation to the AIAA competition. This video will cover the definitions and mathematics. Static stability refers to the tendency of an object or system to return to its original position or state after it has been displaced. It is an important concept in various fields, including physics, engineering, and aerodynamics. Static stability is particularly relevant in the context of static stability analysis of aircraft, ships, vehicles, and other structures. In general, static stability can be classified into three types: stable, unstable, and neutral. A system that is considered stable will, after being disturbed or displaced from its original equilibrium position, return to that position. Think of a ball sitting at the bottom of a bowl. If the ball is slightly pushed, it will roll back to the bottom of the bowl due to the force of gravity. That is also referred to as positive stability. The concept of static stability is crucial in aerodynamics, especially when discussing aircraft stability. Stability analysis involves evaluating the aircraft's response to disturbances such as gusts of wind or control inputs from the pilot. Depending on stability characteristics, aircraft can be classified as longitudinally stable, which is stable about the pitch axis, laterally stable, which is stable about the roll axis, or directionally stable about the yaw axis. Stability in aircraft is typically achieved through careful design of the aircraft's shape, control surfaces, and weight distribution. First, we will start with calculating the slope of the coefficient of moment. To do this, you will need to go to Module, Wing and Plane Design, and then create a plane with both wings, the tail, and masses located along the X direction. This can be done without a tailpiece if you are creating a flying wing, which in order to do so, you'll need to uncheck these boxes. However, most of the time in DBF, we will use a standard configuration plane. Then create a static stability analysis and run it from negative 10 degrees to positive 10 degrees. After that, go to polar view and zoom in on the y-intercept coefficient of moment. It intersects the y-axis at 0.025. And it intersects the x-axis at 1.21 degrees. In order to calculate the slope in terms of radians, we can use this equation pictured here, which is the y-intercept divided by the x-intercept times 180 over pi. However, in order to automate that calculation, we have created an Excel document titled Slope Moment Coefficient Graph, and so we can enter the numbers in here. And that will tell us our final result. The final result is the number in the highlighted yellow box. For the plane to be ideally stable, this number should be in between negative 0.5 and negative 1.5. If this number isn't in that range, it can be changed by changing the size of the tail or by moving the masses around in the x direction. Here we have a design where the mass, an extra mass, has been added near the back of the plane, which shifts the center of gravity backwards. So if we run an analysis for that and go to our polar view, make sure to check that it is visible, we can see that the coefficient of moment line is less negative than the red start line. This means that its number will be closer to negative 0.5, making it a more positive slope. The other edit we can do is to make the tail larger compared to the start one. This one is about twice the size. And so if we run an analysis on that one and go to polar view, check visibility, we will see that it has an even more negative slope than the red line, meaning it's more approximating to negative 1.5 per radian. So making the tail larger will have a more negative slope. Several other details to go over to make sure the plane fits within the general parameters for good flight. The x-intercept value, located here, should be somewhere in between 1 degree and 3 degrees as a general rule. The graph can be shifted up by adding a tilt angle to your elevator, which is pictured here. The larger the tilt angle, the more the graph will shift upwards. For example, we can do that by duplicating start and creating a model with a specifically different tail. Tilt angle. If we move this up to negative 7 degrees, save it, create an analysis, and run that, we can see that the line is the same, but it has been shifted upwards. The force of lift should also be greater than or equal to the weight of the plane at the x-intercept angle. This can be done in two ways. The first option is to go to the inertia tab, find the total mass, and multiply that by 9.8 to get the weight in newtons. You can then analyze the force of lift at the corresponding angle by going to here, and as you can see, it'll be somewhere around 55 newtons of lift, which is more than enough to lift our approximately 2 kilogram weight. The second option is to go to analysis, define a stability analysis, and run that on your plane. As you can see, it creates a little dot in the lift and moment boxes on the x-intercept line, and here represents the weight of your plane. So as long as the line corresponding to that plane is above this dot, you have produced enough lift. Another thing you can do as a final goal is to get the coefficient of lift over coefficient of drag to peak at your stability angle. So here we'll change the graph settings to coefficient of lift over coefficient of drag. And here we have the dynamic stability dot. And so this indicates that we are right around our peak for lift over drag, which is very good. That is the typical goal. If it were lowered down at around 65, that would still be a very successful design, but you can change the shifting angle to get it closer and closer to this peak, which tends to be the shape created for most airfoils in the NACA series. The dynamic stability should always create this little dot here, but you can also still go by like 1.2 degrees and then move upwards to find your cruise angle. That is all I have for this video. Thank you for listening, and goodbye.